Good afternoon, everybody, and welcome to Trench Talk, episode number 4. Today, we're going to talk about the GX Flow Center, a product that has been in the making for 10 years. It's evolved over the years from the GV, the GP, and now the GX. And it has become pretty popular amongst our customers. So without further ado, that's today's agenda. One will describe the problem or the opportunity, as you might prefer to call it. What would be the conventional approach to solve that problem? A little bit about fluid dynamics and understanding the system behavior. Talk about energy, the GX features, our exclusive design support in designing such systems. And of course, I want to hear from you. Either questions or comments are much appreciated. So the premise that the GX Flow Center was built upon was the investment and promise associated with a geothermal system mandates that designs be elegant and efficient. People are spending tens of thousands, hundreds of thousands of dollars to get a geothermal system. It's not just to make them warm or cold. It is to do so with the highest efficiency. That word is synonymous with geothermal. So the problem is, whenever you have a system of, say, 3 or more heat pumps, it's how do you go about developing a pumping strategy that really reflects the type of efficiency and elegance that we want to see in a geothermal system. So here's a picture of a job I visited down in New Jersey. Now, I sold those flow centers, so I was real happy when I got the order. But it is neither elegant or efficient. The total of 7 heat pumps being served. You can't even see all the flow centers on this job. This one right here is actually a 2-circuit flow center. But each one of them feeds a single heat pump. The dual circuit feeds 2. And there are more flow centers out of the field of view of the camera. So a total of 7 heat pumps, each having 2 pumps to serve it. These being non-pressurized flow centers requires that each one have its own dedicated loop field. You cannot put more than 1 non-pressurized flow center on a single loop field. So in other words, you can't have multiple non-pressurized flow centers on a system. And when you do that, you lose the benefit of having a consolidated single loop. There's nothing better than 1 out of 7 heat pumps operating on a much larger loop field under those part load conditions. Although multiple pressurized pump packs can be piped in parallel and used on a consolidated loop field, the energy implications are the same. So let's do some math. We've got 7 heat pumps. We've got 2 circulators on each heat pump. Each circulator is going to draw about 200 watts. If each heat pump operates roughly 2,500 hours a year, you've got the 200 watts times 2 pumps times 7 heat pumps times 2,500 hours. That's 7,000 kilowatt hours, or at 15 cents a kilowatt hour, excuse me, results in over $1,000 a year to operate those 14 circulators. So if Charlie would be so kind to pop up a poll about pump energy, how much pump energy do you think we can save if we had a more elegant solution? I see the results. It's pretty evenly split from 40 to 80%. Give you a minute or two to get some more numbers, more responses. So I appreciate you taking the time to answer our quick poll. Let's go to the next screen. Fluid dynamics. Understanding this is the key to really understanding the energy associated with pumping. So the question is, and this is another poll I want you to just react to, if the pressure drop across the heat pumps and the pressure drop across the loop field are each 20 feet of head at full flow, or 40 feet of head for the total system pressure drop. What is the pressure drop at 25% of full flow? For example, if we had 40 gallons a minute and the total pressure drop was 40 feet of head, and then we were to pump only 10 gallons a minute through that same system, what would the pressure drop be? Get one response so far. I'm going to let you guys ponder this because it provides insight into the dynamics in a system. And you really got to be comfortable with this understanding, not necessarily to do the math, but to have a gut feel about what's happening in a system. You've got two parts to the system. You've got the loop field and you've got the heat pumps, or in this case, combining the loop field pressure drop with the heat pump pressure drop results in the system pressure drop. And as I said, the total system under full flow is 40 feet of head. The loop field, we don't care what the flow rate is. And it's going to follow, the pressure drop is going to follow a typical parabolic curve. And that is, if we cut the flow rate in the loop field in half, the loop field pressure drop will go down by a factor of 4. So it's 1/2 squared, or 1/4. So at 20 GPM, the loop field pressure drop will drop all the way down to 5 feet of head. At 25% of full flow, we're going to square 1/4, or 0.25. And that result is a very low pressure drop, basically 1.25 feet of head when we pressure drop across the loop field when we cut its flow rate down by a factor of 4. So from 40 GPM down to 10 GPM, the pressure drop drops by whatever the math works out to be, but it drops considerably. But the heat pumps, no matter how many heat pumps are operating, whether it's one heat pump at 6 GPM, maybe a 2-ton, that heat pump is going to need that 20 feet of head that any of the heat pumps need when they're operating, whether it's at full flow or part flow. The heat pumps need 20 feet of head to push the appropriate flow rate through that heat pump. So if we go from 40 feet of head at full flow, our loop field goes down to 1.125, and then we have to add the 20 feet of head for the heat pump. So the right answer is 21.25. Congratulations. One person got that right. So to me, this is a vital understanding of picking the right pumping strategy. Now, wouldn't it be wonderful if we had a pump that was smart enough to know this and would adapt accordingly, that when the system's operating at half flow, it doesn't have to create as much head. If it's operating at a very low flow, well, it doesn't have to create even that much head. So it's a smart pump. And lucky for us, there is such a pump. The WILO Stratos MAXO, which is the heart of our GX flow centers, has built-in algorithms into the pump, totally self-controlled inside the pump. So these gray lines are actually represent control lines. And when you're setting up your pump, you put in a head pressure you're looking for at peak flow. And then it will automatically create this control line, putting in 50% or half of your set point at no flow. Now, in our case, we're going to set it up so that this blue line represents our setting on the pump. And it is almost a perfect fit for what our system requires in terms of feet of head at a given flow rate. So this is what translates into significant energy savings, because we're not maintaining a constant head. We're not riding a pump curve. The pump is adapting and optimizing energy consumption. And those energy implications. Here's the actual WILO curve, and they illustrate these angled lines are variable delta P curves that I just talked about. In some applications, you may have to set it up to be a constant delta P. But for right now, ideally, you want variable delta P. And here's that control line that we'd like to use in this application. And then we go to their power curve, and we locate that same control line. And that's what it is, that when you set your pump up to be about 42 feet of head at max flow, and these lines illustrate your setting. So at 26 feet of head, this would be your power curve. At 39 and 3/8, at 42 is our red line. If you set it up for 52 feet of head, your power curve is over here. So it's understanding how to read these power curves that is very helpful. And at 42 GPM, we can see where those lines cross and go over to the right, and it illustrates roughly 490 watts. So at full flow, we're looking at 42 GPM, 40 feet of head for 490 watts. We cut our flow down to roughly 1/4, and now we're looking at roughly 150 watts for 10 GPM and roughly, 21.125 feet of head. Now we can take all this data and plot it. The blue line is the power curve that we just reviewed. But more importantly, you have to also look at the distribution of flow rate throughout the course of winter and summer both. What percent of the time are we only going to have one heat pump operating? Or maybe two heat pumps operating, or three. And every job is going to be unique. You have to sort of understand the load that a heat pump is serving and get a sense for how often it's going to run and do some analysis. But almost every application will have a curve similar to this. Very seldom will every heat pump be running simultaneously. The bulk of the time, you're going to have 1 to 3 or 4 out of 7 operating simultaneously. So understanding this distribution of runtime combined with the power curve, we can then put all this data in a table. And we can look at 6 GPM, it's 120 watts. At 24 GPM, 270 watts. We take the percent of runtime, and this is based on 5,000 hours a year of operation for the flow center. It's a lot more than a single heat pump. Each heat pump will operate roughly 2,000 to 2,500 hours a year, but due to their overlap and simultaneous operation, the flow center would have to operate typically about 5,000 hours a year. We do the math, we accumulate those kilowatt hours, and in this case, our energy for this system is a little over 1,000 kilowatt hours a year. Compared to 7,000 kilowatt hours, that's a savings of 84%. So it's significant, dramatic, cutting operating costs from $1,000 a year down to $150 a year or thereabouts. So let me introduce you to the GX Flow Center. We've got 5 configurations. The basic is just a single pump and one big circuit through the heat pump, through the loop field and back. Then we have the dual. We have 2 pumps in parallel. You can size them to give you full redundancy or partial redundancy, whatever you choose. I'm a big fan of partial redundancy. That allows you to keep the size of the pumps perhaps one size smaller and save some money. So it's a judgment call whether your client wants 100% redundancy where the system can operate on one pump only and meet full flow requirements, or partial redundancy where a single pump might be able to handle 60 to 70% of full flow on one pump. Then we also have primary, secondary. We have 2 pumps in 2 separate circuits. The primary, which is the loop field, would have 1 pump. The secondary, which are the heat pumps, has 1 pump. And you may have to use primary, secondary when the pressure drops of either side or the total pressure drop of both exceeds the capability of our pumps. So if you break it up into primary, secondary, you have a dedicated pump for each half of the system, which you may need to do. I don't think it's preferable over a basic or a dual, but quite often you get stuck in needing that kind of pumping approach. And then we have the dual primary secondary. It's a total of 4 pumps. We've got 2 pumps on the primary side, 2 pumps on the secondary side. And then we just recently set up a special. It's primary secondary. It has only 1 pump. So we have 1 circuit that doesn't have a pump. And we set it up to serve basically our net zero, which has an internal pump already. So in a primary secondary arrangement, the net zero has its own pump providing the secondary function, and the loop field would have its pump on the primary side built into our GX flow center. So what do they look like? Here's the basic, the dual, the primary secondary, and the dual primary secondary, which we fondly refer to as the Spaceship. It is quite interesting looking product. Actually, some of our earlier models of the Spaceship, one of them is installed down in Tennessee at Al Gore's house. And Anna and I had the luxury of going down there and doing a service call on our flow center. So the Spaceship, I want to talk a minute about this design. Dual pump, primary, secondary. We're going to come in from our loop field on the left. These 2 pumps will pump down into a lower manifold, which will go through our canister. It's open to the canister, but directly opposite it is what's feeding our secondary pumps. So our secondary pumps pump up and out this manifold to feed the heat pumps in the system. We come back from the heat pumps and connect to this butterfly valve, which has a straight through leg that goes out to the loop field. But there's a branch circuit off that T that goes right back into our canister, allowing the canister to be a hydraulic separator so we can operate the primary and the secondary at 2 different flow rates. The secondary side will be dictated by how many heat pumps actually have their 2-way valves open and what kind of flow rate is being dictated by the heat pumps. And these WILO pumps will adapt. You'll configure these in a constant delta P mode because you always want X amount of head available to assure proper flow through each heat pump, no matter how many are operating. So you configure these in a constant delta P, and its flow rate will be dictated by the heat pumps. On the primary side, the loop field, we're basically going to use a delta T control so that these pumps will only have to operate at a flow rate driven by a temperature difference that we're trying to maintain. And we use the Grundfos Geo UPC controller to do that. It's pretty simple, pretty straightforward. But I wanted to share this one with you because it can take some pretty large jobs, up to a couple of 100 gallons a minute. So interesting product. Let's look at the anatomy of the GX flow center. We'll start up here at the top, which you don't see in the section view, but there's a pressure gauge up here, 0 to 100 PSI. Even though this flow center operates like a non-pressurized flow center in that there's a standing column of water on the suction side of the pumps to maintain them in a flooded condition. And that is really how a non-pressurized flow center works, but they typically cannot be pressurized. But we intentionally built the GX so that you can pressurize it by design up to 100 psi, but typically your 20 to 40 psi static pressure would be perfectly fine. This allows this flow center to overcome some of the limitations of non-pressurized. A non-pressurized flow center is limited to the height that you can apply this to in a building. Typically about 28 to 30 feet of vertical piping above the flow center is all a non-pressurized flow center can handle. But once you can pressurize this system, now you remove that limitation and you can apply this for 40, 50 feet because you've got positive pressure in the system that allows you to deal with that additional lift in the system. Working our way around, we identified the connection size, in this case 2-inch FPT. We put check valves above each of the circulators. Obviously, there's our circulator, the pump. We have isolation valves on both sides of the pump. For serviceability, you can close those and replace the pump. And they're helpful when you're flushing and filling the system. We do have built-in purge ports. So you can hook a flush cart to this lower purge port and this upper purge port, close your isolation valves, and now your flush cart can completely fill the system and come back out here and not run the water through the pump. All too often, we end up compromising pumps when we're flushing and filling and purging a system because there's possibly some debris that we're forcing to go through the pump and potentially clog impellers or just the volute. We have some adjustable supports because we know not all floors are level. So we can change the height of those to make this stable and give it some support. At the bottom of the canister, we're not picking up the fluid directly from the bottom. So there's sort of a dead space down at the bottom. And any pebbles or debris or anything that's heavier in water has an opportunity just to settle out of the system and remain harmless in the bottom of the canister. We offer both a 6-inch and an 8-inch canister, depending on the flow rates in the application. There's a hose connection, which you don't see in the section view, but if you needed to add water, you could directly connect a garden hose and add water and raise the pressure of the system. The dip tube. One of the secrets to making this reliable is the dip tube. Because our water level is going to be somewhere up here, the dip tube allows the water to circulate without splashing, agitating, creating micro bubbles. So it facilitates maintaining an air-free system as far as the air that's circulating around the system. We have a wall mount bracket to stabilize it. The fluid level, there's a sight glass in the front. Again, you can't see it in the section view, but you want to maintain your water level roughly in the middle of the sight glass. Plus or minus 6 inches, perfectly fine. As long, because that sight glass pretty much reflects the bottom of the dip tube all the way up to the top of the canister. And if the water level fluctuates at all, due to the changing pressures in the system, so be it. Nothing to worry about. The inlet connection size and type. And then this air chamber in the top. You do want to reserve some amount of air in the top. Anything above your water level is an air pocket that acts like an expansion tank. to minimize the pressure fluctuations throughout the year. And for those who like the magic decoder ring to understand our part numbering system, this illustrates that. And Charlie's going to put a link in the chat box to allow you to download this cheat sheet of how to understand our model number system. So there'll be a link to download that from our Dropbox. Also, she will upload another file that contains all the submittals that have been created so far on our family of GX flow centers. Design support. We have put a lot of effort over the years to develop the ability to make selections to meet your needs. Here's an example of a particular project, but I just want to walk you through the type of data we put into this so that when you have a project that we can help you with, this is the type of data we need. So we'll start with the system characteristics. We like to put in the nominal tonnage, the desired flow rate per ton, so it gives us an idea of the flow rate we're looking for. What type of antifreeze, what level of freeze protection, how many heat pumps, how many distribution manifolds. We can come out of our flow center and go into up to 5 different distribution manifolds, and we have to model each one of those. We want to designate the configuration of the flow center. What type of piping are you using indoors? I'm obviously a big fan of polyethylene, but you could use PVC or copper or other material. And each one has its own unique pressure drop characteristics. So we like to capture that. The next area we're going to look at is the loop field. And in the loop field, we have to define the number of groups, the loops per group, and then it calculates the total number of loops. The length of piping. A vertical loop that's 400 feet deep has 800 feet of piping. If it's a horizontal loop and it's only got 600-foot circuits, then you'd put 600 feet here. What diameter pipe is it in each loop circuit? The DR of that pipe. What type of manifold? Is it a buried reverse return or a short manifold interior valve manifold? In this case, it is reverse return, but it's a very short one. It's only 5 feet long with 1 foot between taps. The supply and return pipe going out to each of the 2 groups. So in this case, we have 100 feet of 2-inch pipe. Again, a DR number. The main pipe, once you bring that fluid flow into the building and you combine it into common pipe. So in this case, we're going to have 2 circuits coming in into a 2-circuit manifold. And then that manifold may feed 20 feet of pipe to get to our flow center. So we have to capture that. 20 feet of 2-inch diameter DR11 pipe. The next area we're going to look at are the heat pumps themselves. We have a database of heat pumps, which you can very easily identify a reference number. And that's all you have to do is put in a reference number, put in a tag. If it's on your drawings, we'll use that tag. Otherwise, we'll make up a tag and put something there. And then the database populates all these fields. The manufacturer, the model number, the reference flow rate, and corresponding pressure drop. For example, this is a 2-ton heat pump that the manufacturer chose to put in 10 gallons a minute. I always like to use the highest flow rate that they list as a reference. Gives me a little more accuracy. So at 10 GPM, it has 24.3 feet of head. I then have to decide what size pipe am I going to feed that heat pump with? How long is it? What is a zone valve CV that would be appropriate for that heat pump? Which manifold is providing the distribution to those heat pumps? You can then go in and adjust flow rates on each heat pump and dial in a flow rate that you feel is more appropriate. A 2-ton really only needs 6 gallons a minute. So we're going to dial it down to 60% of our reference. And then the pressure drop of the heat pump is recalculated. So instead of 24.3 feet, if I operated at 6 gallons a minute, my heat pump will have a pressure drop of 8.73 feet. Other parts are calculated. The piping, that 1.25 inches, 40 feet of pipe is calculated. The zone valve, based on the CV value, a pressure drop is calculated. The manifold is calculated. A balance valve, if we need it. And we're going to talk a little bit more about that, but you don't want to use a balance valve on every heat pump because you need to identify the particular heat pump that has the highest inherent pressure drop. And in this case, it turns out to be the 5-ton Sycamore, and we've dialed its flow rate down to 15 gallons a minute, but its pressure drop being 16.74 turns out to be the highest one, and therefore I have to use balance valves on the other 3 to dial their pressure drops in to being roughly equal to that one that doesn't need a balance valve. So all this data, when we're trying to support your designs, we're going to need the schedule of heat pumps, and from there, we will give you this kind of feedback back to you. The next element we look at is a tab. This is the distribution manifold, one of 5 that we could use. In this case, we're only going to use one. And on that tab, you'll see this kind of field that automatically brings over the data from the main page. And all we have to do is put a length of each section of pipe and its diameter that's feeding each of the heat pumps. And it calculates the pressure drop of that distribution manifold, and it's only one manifold. So we end up doubling this to account for a return manifold. But we have to model this. And on your drawings, if you have a plan view and we can identify how long each section of this distribution manifold is, that is very helpful. Otherwise, you're just going to have to tell us the length of pipe between each of the heat pumps. And then we pick a pump. And the MAXOs are the only ones we're going to use on the GX. And those with the Dash X are the ones we've standardized on as part of our standard offering. They're typically the higher head capability pumps. The Dash 50 is 50 feet of head. It's a 2-inch pump. We also offer a 35-foot head in a 2-inch. We offer the 1.5-inch that can produce 52 feet of head. The 1.25-inch pumps, we have a choice between 35 and 52 feet. So we will pick one to make this curve make the system curve fit inside the operating envelope of that particular pump. Next, we summarize all this right in the middle of the sheet. We give you the primary pressure drop or the loop field pressure drop, which is the antifreeze factor, takes all our calculations, which are based on water only, and then we multiply them by the antifreeze factor to give you an anticipated pressure drop with antifreeze. So the loop field would be 17.9 feet ahead at 42 GPM. The heat pump side would be 22.8 feet at 42, a total system of 40.7 feet of head. We also give you an estimated system volume and the amount of antifreeze required to reach the specified concentration. And finally, it automatically gives us the model number of the GX Flow Center and the description. So you can see in this particular case, it's a dual with 2-inch pumps that each could provide 50 feet of head, 8-inch canister, 3-inch flange inlet, 3-inch flange outlet. And then we have another tab, the performance summary. And this is part of the output that we will send to you. And it lists the heat pumps. It also lists the closed loop AHRI rating for both heating and cooling. Lists the GPM that we're going to operate at. We specify a particular two-way valve that corresponds to the CV that we used in our calculations. Gives you the connection size of the valve. We also specify the balance valve that we would like to use. These are FDI valves. They're one of the better valves in terms of having a low pressure drop. And we also provide the value of, if you take a pressure drop across the valve itself in inches of water column, this is the type of reading you would like to get that corresponds to this flow rate. And then obviously we don't need a balance valve on that one heat pump that we talked about. So this kind of feedback is what we will give you to help you set up your system. We've supported over 400 projects. I did a search today in our folder system for files that start GVC, and there's over 400 of them so far. Time for questions and answers, hopefully answers.
So far, no questions, John.
I don't see any questions so far. Come on, did I put you all to sleep? Okay, seeing no questions, I'm going to let you all go home early. I appreciate your time today. And please reach out to us if you have a project where you think the GX would be a good solution for you. We'd be more than glad to work with you and develop a selection for you. So with that, I'm going to say, wish you all a good evening and hopefully see you back here in a month.